folks, how are you? In this video I would like to introduce the idea of the tangent line problem and the derivative. It is possible that you've heard about the tangent line problem before, so we're just going to talk about it again in more detail to set you up to understand that, and then after that define the derivative. So first we've got to talk about what in the world is a tangent line. So think about how you might define a tangent line. What is the picture that you have in your head of a tangent line? And you might say a straight line that touches but does not cross the curve. That sounds like a pretty decent version of the tangent line, right? A straight line that just touches the curve but doesn't cross over it. And for this particular graph, that works. Notice how this is the tangent line. So what you see in purple graphed is the tangent line to this particular parabola. So notice how it just touches but doesn't cross over the curve. But on the other hand, let me show you another graph. Look at this guy. Now, what is drawn here is the tangent line to this point. Unfortunately, you see how it crosses through the graph? Which means our definition of a straight line that touches but does not cross the curve doesn't exactly work, because there's this weird circumstance, and this, you might recognize this, is a cuboid graph, okay? And where that weird little curve is, there is a tangent line, but it crosses over the curve. It's rare, but it does cross over the curve. So then we can do a different definition. What do you think about a straight line that intersects or touches the curve at exactly one point? And that's often what I'll even say for a tangent line. It touches the curve at exactly one point, but it could cross through. That's why I put intersects, because that would still give us the last issue we have. So look at this particular tangent line. So we have a nice circle right here, and the tangent line to the curve at the point, and that's square root of 2, square root of 2. It's just rounded for me. Is right there. That is a straight line that touches the curve at exactly one point. And that's what gives us the tangent line. So it works for this particular tangent line, but you know what's going to happen. It's going to go wrong. Here is a curve with a tangent line, okay? And this looks similar to maybe a negative x to the third polynomial, okay? And what I've got drawn here is the tangent line at the point 1, 2, it looks like. I didn't label it for you. And it's a horizontal tangent line, but it touches here, but look over here. Right here, it crosses right through the curve. So it crosses at 2 points, or it touches at 2 points, either way you want to look at it, and that's the problem with this particular definition. So the point here is we're going to have to be far more specific about our definition. Remember our epsilon delta definition of a limit? And it's because the definition of a limit was so vague, we had to be very rigorous and very specific. We're going to do the same thing with this tangent line story. Although you might find the tangent line problem a little easier to comprehend than that epsilon delta definition of a limit. I hope so. So what we're going to do here is start with a problem. What we want to do is find the tangent line to this curve. Now notice this curve right here, it's a parabola, and I've got it defined right here, y equals x squared at the point 1, 1. Now you can imagine what that might look like. So again, we don't have a formal definition for a tangent line. I'm going to try to draw the line on top of it. And remember, I'm eyeballing it. This is not the true tangent line. I'm just eyeballing it, and I would guess that's what it is. Okay? This is what I'm guessing. And again, a tangent line, we don't have a formal definition, but we know that it needs to touch the curve at that point. And what it's got to do is have the same slope that the curve would have at that point. That's really kind of the idea of a tangent line. So let's see if we can get started on this process. Again, we don't have a formal process, but we're going to work on it and see if we can get this done, and then we'll be able to define a tangent line. Now here's what we're going to do. We will select a point on the graph of y equals x squared, not the point we're trying to find the tangent line, not 1, 1, but some other point. Then draw the secant line. Now remember what a secant line is it intersects the curve at 2 places. We're going to connect Say we pick some point up here and we connect those two dots, okay? And this will approximate the tangent line. Now, it's not going to be right, because it's not going to intersect at two different places, but we're going to try this, okay? So we're just going to approximate the tangent line. So here's what I did. You see it over here in green? I picked the point 2, 4. And if I connect these dots, 2, 4, and 1, 1 with a straight line, there we go, a purple straight line, we can actually calculate the slope of this line, okay? Now, a line is not its slope, but y'all know we can write the equation of a straight line if we know its slope and we know a point on the line. That's all you have to have is the slope and a point on the line, okay? So we can do this. Now, again, you can imagine that this purple line is probably a little steeper than our real tangent line, but it's going to be a reasonable approximation. So let's do this. How do you calculate slope anyway? Y'all know how to calculate slope. Remember the formula? It's y2 minus y1 divided by x2 minus x1. Okay, so y2 on my picture over here is 4 minus y1, which is 1, and then divided by, now if I begin with 4 when I find the slope for my y, I have to begin with x with the same point in the denominator. So this is going to be 2 minus 1. Okay, and 4 minus 1 gives me 3 in the numerator, and 2 minus 1 gives me 1 in the denominator, which gives me a slope of 3. Now, we could even find the equation of that line, but that line is not our line, right? But the slope of the tangent line is approximately 3. Would you guess that to be too big or too small? Remember, slope is how steep a line is. That line is steeper than our imagined tangent line, so my guess is that the slope of the tangent line is probably less than 3, but that's a pretty good approximation. Now you tell me what would make a better approximation. What if I picked a point closer to 1, 1? Instead of 2, 4, pick something closer. And I don't want to say instead of, because we need this first approximation to look at the next, to look at maybe even another one after that. So let's keep going. So let's look this time at the point 1.5, 2.25. I have it right here. Notice I left my purple line. I left that original one. I got rid of the labeled point, but remember that was the 0.24. But now I've scooted it closer. Let's look at 1.5, 2.25. Now, let me ask you this. How am I coming up with this y value? Right? Remember, it's on the curve. So if I scoot closer to 1 with my x's, then all I'm doing is plugging in 1.5 and squaring it to get my y value. Remember, everything on this black parabola curve is y equals x squared. So I'm scooting my 1 closer, and my y value, I'm just plugging it in. Alright, so let's see what that line looks like. Remember, I left the purple one, and now I've got this brand new red one. Now that is a better approximation because I'm closer to the 0.11. Can we calculate that slope? Well, we sure can, right? All we got to do is plug it in. So m is equal to, remember, y2 minus y1 divided by x2 minus x1. My y2 is 2.25 minus my y1, which is 1, and I'm dividing that by my x2, which is 1.5, minus my x1, which is 1. And I simplify this, so 2.25 subtract 1 is 1.25 divided by 0.5 when I subtract in the denominator. And this gives me a slope of 2.5. Now remember, the slope of the purple line was 3. The slope of the red line, which is a little bit of better approximation, is 2.5. Now, is that enough to tell us what the slope of the tangent line might be? No, not really. So let's plug in another point even closer. So what I'm going to do is I'm going to pick, first I picked 2 for my x, and I picked 1.5 for my x. What would you try to pick now for x to get a little closer? How about 1.1? I know that's what you're thinking, right? So we're going to plug in 1.1 for my x. How do I get the y? I take that 1.1 and plug it into the function and square it, and that gives me that 1.21. What am I going to do next? I'm going to graph that line. So notice the purple line was the point that was far away at 2, 4. The red line was the point that was a little closer at x equals 1.5. And now I've got this next line. Look at this guy. The green one. It's even closer, and it's at the point 1.1, 1.21, intersecting with 1.11. Let's find the slope. And Kelly, let's find the right color. There we go, green. Okay, so I'm going to do the slope. Remember, y2 minus y1 divided by x2 minus x1. All right, notice I'm writing that every time to just burn that in your brain. We need to know that. So y2 is 1.21 minus y1 is 1.1. No, it's not. It's 1. Stand by. There we go. Okay, and then x2, which is 1.1 minus x1, which is 1. Of course, I subtract here, and I get 0.21 in the numerator, and I get 0.1 in the denominator, and divide, and that gives me a result of 2.1. Now remember, we got 3 for the first slope, 2.5 for the second slope, and 2.1 for the third slope. And remember, I left all those lines there. Now, what would you guess, maybe? Do we have a good guess of what the slope of the tangent line might be? Is 3 lines enough to approximate it? Well, what would make a better approximation? You know the answer to this. What am I going to do? I'm going to maybe scoot closer, even closer to x equals 1 than I was at 1.1. What would be even closer? Well, how about this guy right here? 1.01 for my x. Now to find the y, I take that 1.01, I substitute it into y equals x squared for my x value, and that spits out 1.02. Now remember, that is on my parabola, my black curve right here. These lines are my approximations. The purple one was the first one, the red one was the second one, the green one was the third one when we did 1.1. Now I'm going to try 1.01. Now watch me connect the dots here. It's hard to even tell the difference between the two dots, by the way. The purple one is the 1.01, 1.02, and the red one, which you can barely see underneath it, is the 1, 1. And then the black line. I made it black so you can clearly see what's going on. I think I changed the color later. But the black line is our new approximation. Now, this thing ought to be super close to the tangent line. Don't you agree? It's still not. It's a secant line. But we're going to find the slope of this guy. And I use my formula. I know you're tired of me writing it. y2 minus y1 divided by x2 minus x1. That is just the slope of a line when you know 2 points. So I do know 2 points. I know my y2 is 1.02 minus my y1, which is 1. And then x2 is 1.01 minus my x1, which is also 1. I subtract in the numerator, I get 0.02. I subtract in the denominator, I get 0.01. When I divide that out, I get 2, which is a problem to me because I know that's not right. You want me to tell you why I know that's not right? Because the slope of the tangent line is 2, and we're getting closer and closer. Now, here's where it went wrong, and let me tell you in case you make this silly mistake. Some of you are number crunching while you watch this video. Good for you. When you plug in 1.01 into y equals x squared, you don't get 1.02. Now, I'm going to be honest with you. This is not really my error. This is my error in going back and looking at my work. But when you type that in, it's 1.0201. But what happens is when Desmos plots a point, they round it. And then even when it's labeled, it's rounded. So I have to be careful. This should be 1.0201 in the numerator, which when I subtract, that is also 0.1. And then when I divide, I get 0.0201 divided by 0.01. And I get 2.01. That's the answer that I'm looking for. Okay, so remember the first slope, we got 3. then we got 2.5, then we got 2.1, and finally we got 2.01. I could pick a point closer. You know I can, right? I could pick 1.001. I'm not, because I think you got the point by now. Now, what's the lesson you learned from this mistake that I just made? Is don't round. Please don't round in the middle of this problem. If it goes out 10 decimal places, then you need to go out 10 decimal places when you're doing this, okay? And this is a short-lived problem. You're not going to be doing this problem all the time in further sections, just this section. But we're getting closer and closer and closer. That's the point. What does that mean when you get closer and closer and closer? That's a limit, y'all. You know that. That's a limit. And we've done an entire chapter on limits. And so that brings me to right here. It says recall the slope values for the secant lines. It's 3, 2.5, 2.1, and 2.01. Okay? So it says what is the limit of the slopes of the secant lines? And so you would tell me that the limit, it looks like it's getting closer and closer to 2, right? And that would be the right answer. That limit is getting closer and closer and closer to 2. Now notice we only took the slopes of points on the right. We could have done this on the left as well, and it still would be a limit of value of 2. Now it says, what is the equation of the tangent line? Remember, we just found the slope. How do we find the equation of a tangent line? Now, you might have done this two different ways. You might use the point slope, which is y minus y1 equals m times x minus x1. A lot of you guys have seen that before, where you plug in your point, which is x1, y1, and you plug in your slope, which is m. Or you might just do the efficient thing and go to y equals mx plus b, and you might say, I don't know what b is. That's the y-intercept, right? Not a problem. We can find b. We do know the slope is 2. So now we have y is equal to 2x plus b. We still don't know b. How do we find it? Well, we need a point, x and y. What is our point? Remember, that's 1, 1. Not the points I'm getting closer and closer to. I mean in the original problem for the tangent line. We're trying to find it at 1, 1. So we got this. My y is 1. 2 times my x is 1 plus b. And I solve for b. So I subtract 2 to the other side. So I get b is equal to negative 1. Okay, so that means my answer is y is equal to 2x minus 1. Okay, let me go look at all these lines stacked up and see if 2x minus 1 seems reasonable to you. So I backed up a page, look at there. Now remember, the black line is still an approximation, but it is so close that we're almost right on it. And look at the line. So the slope, they're saying, is 2. You rise 2, run 1, rise 2, run 1. See how the black line almost meets that because the slope's 2.01. And look down here, the y-intercept looks like negative 2. It's not. Look, there's negative 2 right there. So that would be negative 1 right there. Now remember, the black line's an approximation. It's off just a touch, but it's very, very close to the point where I'm not going to graph the real tangent line. So this is how you would find the equation of a tangent line. And I'm going to go ahead and tell you the hard way. There's an easier way to do it. We're about to develop that. But this is a method, and you've done this method before probably in an earlier section. And now we're revisiting it for real in our Calculus 1 class. Now let's take a look at this formula. This is the slope of the secant line. A way we could write that is m just subsecant. You could abbreviate that too, but the secant line, remember, is the one that intersects at 2 points. Now this doesn't look like anything we just did a minute ago, does it? It says f of c plus delta x minus f of c over delta x. I know you can read that where the triangle's that delta x. Remember, delta means the change in something, and so delta x means the change in x. Computer's not acting right. I apologize. Now, if we have the change in x, here's what we're used to thinking about slope as being, right? Is m is equal to y2 minus y1 divided by x2 minus x1. That's what we're used to thinking about. But now let's talk about this. First of all, y values, right? So y values are just function values. So I could think about this as f of x2 minus f of x1 over x2 minus x1. That's more like notation that we have going on instead of saying y values. Now, this x2, it is just a distance away from x1. So if I go back and do a quick sketch of my parabola right here, and here's the point that we were looking at, and that point is C, f of c. Now for our problem, we said it was 1, 1. But the x is 1, the y was f of 1, which was 1 also. And we're picking some point here away. Now what delta x represents is the distance between C and this next point. So this was C2, okay? Or the x1 and x2. And this is delta x, y'all, just the distance away. So instead of saying f of x2, we're saying f of your first x value, we're going to call it c, plus that little distance away gives us our next x value. So that's all that is. How far away from the original x value is the new one? Minus the original x value, which is f of c. Now that's no different than saying x1, right? We're just calling it c instead of x1. Over. Now, at the bottom I have x2 minus x1. Remember x2, here's what we called it. We called it c plus delta x, didn't we? Because it was c plus some distance away, and then minus c. Well, y'all, that just gives you the distance delta x. So this is just a different way of thinking about y2 minus y1 over x2 minus x1. Instead of naming the next point, we just look at it as a distance away from C. Okay? That's our secant line. And that's what we did every time. But instead of saying how far away from C are we going, we just picked another point. Now let's take a look at this loveliness. So the slope of the tangent line is what we're trying to build. Okay, that's what we're still working on right here. But we have the slope of the secant line. Remember, we just explained where that came from. F of c plus delta x minus f of c over delta x. That's no different than saying y2 minus y1 over x2 minus x1, and that's just the distance they are away. Now the definition of the tangent line, which is all that work we did a minute ago, is the limit as that distance goes to 0. Now, one way of writing that is the change in y's over the change in x's. That's what we did every time. You know, y2 minus y1, that's just the difference in the y values. x2 minus x1 is just the difference in the x values. Now, the better definition, the more useful definition probably, is this guy that we've got going on here. Now, remember, that's the same as the secant line slope, but we'll take the limit as delta x goes to 0. What does that mean? The distance away from x gets smaller and smaller and smaller. That's what we did by drawing all those lines, and they approximated the slope. So, turns out the slope of the tangent line is just a limit. And it's a limit of taking the slope of all of these secant lines where the distance between x and the next point you pick is smaller and smaller and smaller. Then it says the line passing through the point, remember that's when we actually found the equation of a line, and is with slope m is the tangent line. So you're fine, this is the slope of the tangent line, okay? And the tangent line is actually when you find that equation. Okay, you want to try this? We've got this. It's easier than just picking these points and getting closer and closer. You can just use a limit instead. And before we try this, I do need to point out that the equation of the tangent line is y minus f of c equals m times x minus c. Now, y'all, don't get hung up with this definition. You can say that's no different than saying y equals mx plus b. And when you find your m from the blue block here, you just plug it in, and then you use your point, your c, f of c, to find the y-intercept. Or this is y minus y1 equals m times x minus x1. Okay? Just a different way of writing it. That's all it is. Yay! Let's do a problem. You ready? Okay, so that first official problem we did is basically to explain where that definition came from. So I left our definition over here in blue so we can take a look at it. But we're supposed to find the slope of the function 5x minus 1 when c is equal to 3. You've got this, okay? So we're supposed to use this definition that I have right here. I just circled it off. We're going to take the limit as delta x goes to 0. That will always be the case. That will not change. Of f of c plus delta x. Now, right now, you can leave that as c plus delta x, or we could go ahead and plug in 3. Let's go ahead and plug in 3. So this is going to be 3 plus delta x minus f of c. So that's going to be f of 3 over delta x. Let's keep simplifying. So this is the limit as delta x approaches 0. Now, we have a function, don't we? Our function is 5x minus 1. So let's do what this says. This says we take our function and plug in 3 plus delta x. So that means I'm going to have 5. I'm going to remove the x and replace it with 3 plus delta x minus 1. So 5 parentheses 3 plus delta x minus 1 is just f of 3 plus delta x minus f of 3. So I'm going to use parentheses and plug 3 into that function. That's 5 times 3 minus 1, and that's all divided by delta x. I keep going. It's all about simplifying now. So I have the limit as delta x approaches 0. In the numerator, I have 15 plus 5 delta x minus 1 minus 15. You could go and say that's 14. That's probably the smarter thing to do, but I'm just going to distribute. That's plus 1, which of course is minus 14 over delta x. I'm going to add like terms. The limit as delta x approaches 0. Now look at this. This 15, I'm sorry, cancels with this minus 15. This negative 1 cancels with this plus 1. And I'm left with 5 delta x divided by delta x. Okay, remember delta x is a single variable. Don't think that's delta times x. It's not. It's just one thing. It's delta x. The delta x's cancel, and I'm left with the limit as delta x approaches 0 of 5. Now, we already know the limit of a constant, no matter what you are approaching, is that constant. So here's what we just found. The slope of the tangent line is 5. Now, since we found the slope of the tangent line is 5, I want to talk about it in terms of this particular problem. This shouldn't be a big surprise to you. So first of all, if we graph f of x equals 5x minus 1, now we know what that thing looks like. That is a straight line with the y-intercept at negative 1. My slope is 5, right? So I probably didn't scale this right, but I rise. So here's my y-intercept. I rise 5. 1, 2, 3, 4, 5. Just imagine, and I run 1. Okay, so that's the next point. Again, I would rise 5. 1, 2, 3, 4, 5. Run 1. This is my line. Now, what we were asked to do is find the slope of the tangent line for c equals 3. So it would be over here somewhere. Now, that means it keeps going up forever. Now, at the point 3, remember this is the point 3. If you plug in 3, you get 14, right? What is the slope of the tangent line right there? Well, if I drew the tangent line on it, it's going to look just like my straight line already, because the slope of the tangent line of a straight line is just the slope of that straight line. No surprise that it's 5. It gets more interesting when you don't have straight lines anymore and you have curves, but we had to start small, right? So that's what we just found, and let's try another one and just build our skills. Okay, so question B, find the slope, and again I should say of the tangent line. I'm not going to write it in there, but we're finding the slope of the tangent line of the function f of x equals 2x squared. You know what? We know what that looks like, right? 2x squared is a parabola. The 2 kind of stretches it out a little bit so it's more narrow. And the point C is equal to 1 about here, so we're trying to find the slope of that tangent line. We know it roughly looks like that, but roughly doesn't tell us anything for real, right? So what we're going to do is we're going to use this definition. So I'm going to take the limit as delta x approaches 0 of f of, now my c value is 1, so 1 plus delta x minus f of 1, because that's my c value, all divided by delta x. Now remember what that finds. That's going to find the slope of the tangent line. And that's all this problem asks for, is what is the slope of the tangent line. So I continue to simplify. I have the limit as delta x approaches 0. Now we know what our function is, so I'm going to substitute, first of all, 1 plus delta x right here where there's an x. So I'm going to remove that x and replace it with 1 plus delta x. So that's going to give me 2 parentheses 1 plus delta x, that's all squared, okay, and then minus f of 1, so that's going to be 2 times 1 squared. And here's my advice, always put brackets or parentheses when you subtract the f of c value. In this case, there's only one term in our function, so we would not have gotten it wrong had we left that off. But usually you have more than one term. So let's go ahead and get in the habit of putting parentheses when you subtract, when you do this part, minus f of c. Now it's all about simplifying. So we're taking the limit as delta x approaches 0. Now here's the thing, I have to FOIL this 1 plus delta x squared. I'm going to multiply 1 plus delta x times 1 plus delta x. If you need me to, I'll write it down. 1 plus delta x times 1 plus delta x. That's what's really happening. Minus, now we know 2 times 1 squared is 2, so I'm just going to put a minus 2 out there. All divided by delta x. I'm going to use the FOIL method to expand that binomial. So here I go, 1 times 1, of course, is 1. 1 times delta x is delta x. Now keep in mind, delta x is just one variable. It's not delta times x, it's just the name of one particular variable. It's delta x, and it's termed the change in x. So another delta x, and then this is delta x squared. Okay, remember that's just the one thing squared, minus 2. And that's all divided by delta x. The very last step will be taking the limit. So right now I just continue to write that limit in front so I don't forget about it. Okay. Now I can add like terms. So we have some like terms right here. Delta x plus delta x is 2 delta x. And I also can distribute the 2 inside. So of course 2 times 1 is 2. Now, I'm going to go ahead and add this in my head. That's 2 delta x times 2 is going to give me 4 delta x plus 2 delta x squared, and then minus 2. That's all divided by delta x. I continue. That's the limit as delta x approaches 0. The 2 minus 2 cancels. So now I have 4 delta x plus 2 delta x squared divided by delta x. And if you think about it, you might be wondering why I'm doing all this simplifying. Why am I doing all this? When you take a limit, can't you just substitute? So as soon as we got here, what would happen if I just substituted delta x? Well, I know one thing. I'd get a delta x equals 0 in the denominator, and we don't want a 0 in the denominator. We need to simplify these completely before we take the limit, okay? I never did address that, but I want to make sure you realize if you try to plug it, even now, if I try to substitute in delta x, I'm just going to get 0 over 0, which is bad news. So I have the limit as delta x approaches 0. Now notice there's a delta x in both of these terms. I'm going to factor that guy out. This one, and then one of those guys is going to come out front. And that's going to give me delta x times 4 plus 2 delta x. Remember, that's squared, so one of them remains, divided by delta x. Now, the good news is, look at there. That cancels. So I am taking I'm going to highlight this for you. I'm taking the limit as delta x goes to 0 of 4 plus delta x. Ooh, that's bright. Sorry. Okay, so when I'm allowed now to substitute in 0, Why? Because I have a continuous function over here, or you can think about that as a polynomial using the substitution rule. That's going to be 4 plus 2 times 0, which is 4. What did we just find? We found the slope of the tangent line. Now, we didn't find the equation of the tangent line. I haven't asked for that yet. We just found the slope. So this is m of the tangent line. Okay? This takes practice. Let's try another one. So before we jump in and do another problem, I have the formal definition of a derivative. So I know you've heard the term derivative before. In your math courses in high school, it's quite possible that you've found derivatives. You've used some of the properties of derivatives, or maybe you even did it this long definition way. But that'll look familiar to you. The derivative really is just the slope of the tangent line. And remember, all the slope of the tangent line is the limit as your delta x, which is the change between your c and a close value to c, a close x value to c. And as that gets closer and closer to 0, you're finding the slope of the tangent line. So the derivative is simply the slope of the tangent line. Got lots of notation for this derivative. So first of all, notice this f prime of x right here I'm highlighting. That's a notation that you'll see all the time. Okay, so then that means find or calculate the derivative. Another way down below, so there's the f prime of x that we use, and I read that f prime of x, but it really just means the derivative. You will also see dy over dx. That comes from the idea of delta y over delta x. That's the change in y over the change in x. And it's a rate, okay? And remember, the slope is just simply a rate. It's the change in y's over the change in x. And when you use this notation dy over dx, it represents the derivative, and that's an instantaneous rate of change, okay? Another notation that you'll see is this y primed. So it depends on the name of your function. If we call our function f of x equals, we would use f primed of x. Instead, if we call our function y equals, then we could use y primed. Here's something else you'll see later down the road. It's the derivative of f of x with respect to x. Okay, so again, this with respect to x or dx, I've read it two different ways, but this is the derivative of y with respect to x or dy over dx. You'll hear it both ways. This is the derivative of f of x with respect to x or derivative of f of x over dx. And it's talking about the limit as the difference between a fixed value and the value getting closer and closer to it. That's happening in the x-axis. And finally, this also means the same thing. This is the derivative of the function y with respect to x. When you take maybe a calculus 3, you will see notation in this format. You may see it in this semester, but I don't think that comes up very frequently. But f primed of x, dy over dx, y primed, and even this notation we use very frequently. So again, notice here, dy over dx is the derivative of y with respect to x. And then down here below, it says, so dy over dx is the limit as delta x goes to 0 of the change in y over the change in x, or we could read that delta y over delta x, but delta just meaning the change in those. We've seen this already. That is the slope of the tangent line, right? And that is what this definition is. So the derivative, this is not a new definition, just a new name. The derivative is the slope of the tangent line, which is the limit as the change in x goes to 0 of the slopes of the secant lines. Really, and that's a summary of this whole video so far. Okay, so for problem C, we have some new directions. Find the derivative using the limit process. In orange over here, I have the limit process. Now, this is not any different than finding the slope of the tangent line. Notice the definition is exactly the same. We just have this extra f primed of x notation. So here we go. So f primed of x is equal to the limit, okay, as delta x goes to 0. Now, I say it's not any different. It's a little different because we don't have a c value. And that's okay. You don't have to have a c value. Notice it just says f of x plus delta x. So x would be any c value, and we're just going to leave it as x instead of plugging in a particular c value. So here we go. F of x plus delta x. Now let me just write the definition down first. X plus delta x, okay, minus f of x over delta x. Alright, so I'll come over here. I'm going to need a little bit of room for this. We have the limit as delta x approaches 0. Now remember what f of x plus delta x is. That means to substitute x plus delta x everywhere there's an x in your function. So I have to plug in x plus delta x in both of those positions. If you remember from a pre-calculus course, this is called the difference quotient. And this is exactly why we practice that in pre-calculus. So you have x plus delta x to the third, alright, plus x plus delta x squared. Now that is x plus delta x. If you're already thinking, oh no, are you kidding me? Do I have to multiply all that out? Yes, you do. So minus f of x. Okay, now f of x is the original function. This is where I warned you that parentheses or brackets are needed. In this case, required. Okay, all divided by delta x. So I'm going to come underneath, and I'm going to begin simplifying this thing. We may have to add a page, a blank page to get our work finished, and that'll be okay. So I need to expand x plus delta x to the third. That's a lot, okay? If you have studied the binomial theorem, that you will have a good idea of what x plus delta x to the third is. I'm going to go ahead and put my delta x on the bottom here. I may have to make that line longer before it's over with. But if you imagine, and we could do it over here and maybe erase it, x plus delta x times x plus delta x times x plus delta x. So again, if you study the binomial theorem, you can just use that. If not, you might not want to expand it all out. Let's do that for those that need it. Alright, so here's what I'm going to do. I'm going to multiply these two guys out first because I can't do this in one swoop unless I use the binomial theorem. So the x plus delta x in the front, I'm leaving it alone for the moment. X times x is x squared, right? X, we already know this. We've done it. X times delta x is going to be x delta x. I say we've done it. We did it when there was a c value. So let's be more careful. X times, and then delta x times x is another x delta x. Notice the dots because I want you to realize delta x is not multiplication. It's just one thing. So we're multiplying x times that one thing, delta x. And finally, delta x times delta x is delta x squared. I'm going to add these like terms. So that's x plus delta x times x squared plus 2x delta x plus delta x squared. Now I'm not finished, right? I have to distribute this x inside and this delta x inside. So x times x squared is x to the third. X times 2x delta x, be careful there, is 2x squared delta x. And then x times delta x squared is just that, x delta x squared. Now I'm multiplying delta x times everything. So delta x times x squared is x squared delta x. I'm running out of space. I'm going to come down here. Plus delta x times 2x delta x is going to be 2x delta x squared. And then delta x times delta x is delta x to the third. Isn't that fun? Now I'm going to add like terms. When I add like terms, y'all, I'm going to go ahead and move it over here to this line. So x to the third, there's not another one. So that's 1x to the third plus. Now this 2x squared delta x, there is another one. It is a 1x squared delta x. That gives me 3x squared delta x. That's just one term. Plus, now this x delta x squared plus a 2x delta x squared is 3x delta x squared plus delta x to the third. Wow, right? That's a lot, y'all. All that is x plus delta x to the third. Now I have to expand x plus delta x squared. Now the good news is I already did that. I did that in the middle of doing the big one. So that is what that is. Now what I'm going to do is take a moment, just hang tight, and I'm going to copy this in for this position, and then I'm going to erase all this over here. I'm going to erase what we don't need now. Again, if you didn't get all that expansion, just pause it. Make sure we're on the same page. Just a lot of algebra, right? Just a whole lot of algebra and simplifying polynomials. So I'm recopying this x plus delta x squared, which was part of our solution a minute ago. So that's plus x squared plus 2x delta x plus delta x squared. Now again, forgive me, I'm going to erase this scratch work here because I would like the space. I don't feel like you ever have to do that on paper. It's better to have it. I distribute this minus sign, so that's going to be minus x to the third minus x squared, and then all over that delta x. Now once you do all that, then the fun begins. You simplify. Delta x goes to 0. And here's a hint. What should happen, especially if you're dealing with a polynomial, is all of your terms without a delta x should cancel out. Okay, so I'm going to do this canceling in a different color. X to the third cancels with negative x to the third, right? X squared cancels with negative x squared. Now that didn't help a whole lot. We have a whole lot left, but let's check out what we have left. What we have left is every term has a delta x in it. And remember, our ultimate goal is to plug in delta x equals 0. So I need to factor out this common delta x. So that one's going to come out of the 3x squared, and that's going to leave 3x squared, plus one of those, because it's delta x squared, so I still have 3x times delta x. One of those, so that's going to be delta x squared. 2x delta x, that entire delta x comes out and leaves 2x, and at the end, plus delta x. Now it's possible we had some like terms in there. I really didn't pay attention to that like I should. No, there's no like terms in there. Okay, so the delta x's cancel. That is the important part of this, because my next step is to substitute in delta x equals 0. Now watch this cute trick. I'm going to write right on top of our problem because we have space issues. So the next line I would rewrite exactly what I have here, but you know what? This delta x right here is going to be 0. This delta x right here is going to be 0. And this delta x right here is going to be 0. Remember, these have already canceled. That's gone. Now, if those values are 0, when I take my limit, then I'm left with 3x squared, remember that's 0, plus 0, plus 2x, plus 0, which is essentially 3x squared plus 2x. And since I've taken the limit, I don't like the limit anymore. As soon as you substitute this value in, or you evaluate the limit using some other method, then that is your result. So here's what we found. We found the derivative of x to the third plus x squared is 3x squared plus 2x. Awesome, isn't it? It's a lot of algebra, but you've got this.